All going well, this is the last video of the course, and I will get to a proof of Szemerédi's theorem for progressions of length 4, using, of course, everything that we've done up to now. So let's just see where we'd got to at the end of the last video. We had this inequality here, C3, so just a quick reminder of the setup. We had a set A that lived inside G, which we were now taking to be fp to the n, although quite a lot of the argument worked for a general finite abelian group, sometimes with order not divisible by 2 or 3. And we assumed, first of all, so we have the density of A was delta, and we dealt first with the case, and f was the balanced function of A, and we dealt first with the case where f had a small u3 norm, in which case we could see that A, or could show that A contained progressions of length 4. And so then we started investigating the situation where f had a large u3 norm, which in fact specifically we took its 8th power to be at least some constant c. The c coming out of the first part of the argument. And by a succession of arguments, we ended up establishing that for some constant c3 that depends only on c, it was at most the average over all x, a, and b of f1 of x, f2 of x minus a. Oh, sorry, I want to get to this line here, sorry. So the average over a random, we managed to find a symmetric bilinear form sigma and a subspace V of bounded codimension, so codimension depending only on C, such that if you take random translates of the coset V by U, V, and W, and then look at this average. So it's something that looks a little bit like the expression for the 4th power of the U2 norm, except that we're sort of twisting it by this bilinear phase function here. Then that average is large. And what we're going to see is that now that we've got a symmetric bilinear phase function, we can apply a polarization identity to pull out some quadratic phase functions and stick them in the f's here. So let's see how that's done. So if we set qx to be sigma xx over 4, so one normally sets it to be over 2, but we've already got an over 2 here, so we're going to have to make it over 4. Then sigma ab over 2 turns out to equal qx minus a minus qx minus b plus qx minus a minus b. And you can check that very, very quickly. You just substitute in and out it comes. So we can rewrite this expression as, so let's just have a new inequality. So it's at most average UVW, and then we've got all these averages, which I better write out again. V plus U average A in V plus V average B in V plus W of, and I'll say what I'm talking about in just a moment, so G1 of x, G2 of x minus A bar G3 x minus B bar G4 x minus a minus b, and I've got enough space because I'm stopping there. And what have I just done? Where gi of x equals fi of x omega to the minus q of x. So why is that? It's because if you stick that, if you just substitute fi of x omega to the minus qx into here and see what you get, then you get a big omega to a big expression, and what you get is minus this thing here, so it equals minus this, which is exactly what we wanted. So this really does equal this, but now we've got something nice, because this is just one of those U2 inner product things, and we can use a generalized U2 Cauchy-Schwarz inequality to say that that is, so I'll put that in brackets, say that this thing is less than or equal to the average over U, V, and W of what I will call G1 of U, G2 U minus V, G3 U minus W. I'll explain what these functions are in a moment. U minus V minus W, where Gi of Z is the restriction of Gi to V plus Z, and the U2 norm is measured inside V plus Z. So when I say inside V plus Z, what I mean is you could think of the restriction of Gi to V plus Z as being a function that equals Gi inside V plus Z and 0 everywhere else, and then all those zeros would bring down the average, but that's not what I mean. I mean I just take the average over additive quadruples that are inside V plus Z. So there I've just applied the generalized Cauchy-Schwarz inequality, but now I'm going to use the fact that these functions Gi have L infinity norm at most 1, which implies that they have U2 norm at most 1, to argue that this is less than or equal to well, U and V, U minus V just ranges over everything, so I'll just say it's the average overall. I'll call it U again, because if I write Z, then Z looks a bit too much like a 2, so I'll just say average over U, G2U, U2, which it's going to be convenient to say that implies C3 squared by Cauchy-Schwarz again is less than or equal to average U2 squared, because the average of the squares is at least the square of the average, which is at least C3 squared. But we also have that for any function on any space, we have that, so this is not the same f as before, this is a sort of general statement, that this is less than or equal to, as long as f has L infinity norm at most 1. And if we don't want to put that a condition, we can just add in this f2 squared thing. So that inequality is true for all f. If f has L infinity norm at most 1, or even L2 norm at most 1, then we can just get rid of this on the right hand side. So using that inequality, that implies that C3 squared is less than or equal to the average over U of G2U hat infinity, because the square is bigger than the fourth power, so the infinity norm is bigger than the square. So for each U, we can pick some R of U such that C3 squared is less than or equal to the average over U of G2U hat of R of U, which equals average over u of average over x, g2u of x omega to the minus r of u dot x. But what was g2 of u? It was the restriction of g2 to v plus u. So we can write it like this. It's the average of u, average of, so this is, well, let's just write that more explicitly. X belongs to v plus u. And then g2 of u was f2 of u times omega to the minus qu. Now, sorry, g2 of x, I mean. And f2 of x is just f of x, and that's why I chose 2 rather than 1, because g1 of x was not f1 of x, it was f1 of x multiplied by some linear phase function. So I can say that this is f of x omega to the minus q of x minus r of u dot x. Just quickly check that I've got my expression right. Yes, that looks okay. So this is giving me something very interesting about f, which is that on this coset of a subspace, f is correlating really quite well, at least on average, with a quadratic phase function. By quadratic phase function, I just mean omega raised to the power some quadratic function. And so let's just say, so in particular, there exists a u such that C2, 3, wrong way around, C3, 2 is less than or equal to the average x in v plus u f of x omega to the minus qx minus ru dot x. Now what I want to claim, although this is not necessary, actually if you want to be really efficient as far as bounds are concerned, it's better to use this thing that we've achieved here. But I'm not going to do that. I'm going to show that we can get f to correlate with a globally quadratic function in a rather artificial way. So what I'm going to do is to say so let W be a complementary subspace to V, and then every vector can be written as I'm going to write it as the following: U plus V plus W for some V in V and W in W. So normally we would write it as without this U here, but I want W to be 0. When W is 0, I want to be inside this particular translate of the subspace. So now pick a random Z and define Q Z of U plus V plus W to be Qx plus RU dot X. Sorry, that's not what I want to say because we don't know what X is. What I want to say is Q of U plus V plus RU time of U plus V plus Z dot W. So then the average over all Z of Q of omega to the QZ of U plus V plus W equals, so when we take the average over Z, if W is a non-zero vector, then this average over Z dot W is going to be, oh sorry, pick a random Z in W. So if W is a non-zero vector, then the average dot product with Z is going to, the average, when I expand this out, I'm going to get an expression that doesn't depend on Z multiplied by omega to the Z dot W. And the omega to the Z dot W part will average 0 if W is non-zero and 1 if W equals 0. So we get 0 if W doesn't equal 0 and omega to the Q U plus V plus RU dot U plus V otherwise. And so since the probability that Z equals 0 is P to the minus R, where R was the rank of the bilinear form which was bounded, so R equals the dimension of the complementary subspace, or the codimension of V, which was small, but the dimension of W. We get that P to the minus R C3 2 is less than or equal to the average over Z of average X in V plus U f of X omega to the minus Q Z of X. Except that's not the average over, that's average over all X. And so therefore there exists a Z such that the average over X, f of X, omega to the minus Q Z of X is greater than, well, let's call it C4 now. So we've managed to get correlation between f and some quadratic form, which what I basically did was I took the quadratic form that I had on the coset v plus u that correlated with f, and I just sort of added some random linear part to it, and then sort of said that on average f globally correlates with that random quadratic form, because on average the other parts are 0 and we still have the correlation on the small coset, and that's why this extra factor p to the minus r comes in. So that part's not actually terribly important because we can do without it, but it is. We have got actually a nice theorem here, which was that which is building on previous arguments. This theorem is due to Green and Tau. So let's just quickly highlight what we've got here. We've got that if f infinity is less than or equal to 1, and fu3, I'll still make it to the 8, is greater than or equal to c, then f correlates with omega to the q for some quadratic q. And this is sometimes called quadratic Fourier analysis, because we've seen something similar. If the U2 norm is bounded below, we get correlation with omega to raised to the power some linear function. Here we get a quadratic function. What we don't have is a decomposition of f in terms of quadratic functions. So that's slightly frustrating, but there's no nice known way of doing that. So now what are we going to do? Well, we're almost done actually, but so in the linear case, going back to Roth's theorem, when we had correlation with a linear function, we then argued that that linear function was going to be constant, or roughly constant, on a whole lot of nice sets. In that particular case, it was arithmetic progressions. Here we're going to do something rather similar. So I'm going to prove a lemma that says that if I've got some quadratic function, it must in fact be that we can find a partition of fp to the n into quite large subspaces on which it's not just almost constant actually, but exactly constant. So here comes a lemma. Let sigma be a symmetric, I may not need it to be symmetric, but it's sort of convenient, bilinear form, then fp to the n can be partitioned into subspaces of dimension at least n over 2 minus 2, affine subspaces that is, otherwise there wouldn't be much chance, on each of which sigma is, well, on each, such that on the product of any two of them so in particular, if you take just one of them and you look at the quadratic form that you build out of sigma, namely sigma xx, that will also be constant. So let's quickly see how to prove that. So the first part, of the proof, I will not really prove all that carefully, although in the notes it's done a bit more carefully. So first, note that for any three-dimensional subspace, there exists well, let's call it, I'll still call it V. There exists X in V, well, no, I'll call it X actually. There exists X in X such that sigma XX equals naught. So why is that? That's because what you can do is take your three-dimensional subspace and diagonalize the quadratic form QXX. So we can pick we pick a basis UVW such that Q of UVW is lambda squared U plus mu squared V. That's not what I wanted to say. Q of lambda U plus mu V plus nu W equals A lambda squared plus B mu squared plus C nu squared for some coefficients A, B, and C. And when we've done that, we note that if any of A, B, and C are 0, then we've got our vector. Say if A was 0, then that would tell us that Q of U, for example, was 0. So we'd be done. That's Q of X equals sigma XX. But if none of those are 0, if none of A, B, and C are 0, that's saying, can we find 3 quadratic residues such that A lambda squared plus B mu squared plus C nu squared is 0? And the way you can prove that is to say, well, let's look at the set of non-zero residues multiplied by A. So that'll either give us all the residues or all the non-residues. But that's a set of size p minus 1 over 2. And here we've got another set of size p minus 1 over 2. So when we take the sum set of those two, we'll get a set of size at least p minus 1 over 2. But actually, since it's not a subgroup or even a coset of a subgroup of Fp, then actually you must get strictly more than p minus 1 over 2 points. And here, if I let nu squared range over all quadratic residues, including 0. Sorry, here I was taking non-zero residues, lambda squared and mu squared. But if I let nu range over even the 0 quadratic residues, I've got another p plus 1 over 2 points, and so I must get some, one of these must be minus one of these, and so I've got a non-trivial combination giving me 0. So an argument like that says that we can, in any 3D subspace, we can find such a thing. This, by the way, I mean x not equal to 0. Once we've got that, we can do an inductive argument. So we'll operate as follows. So pick x1 such that q of x1 equals 0, and let x1 be the set of all x such that sigma x1 equals x dot x1 equals 0. So sigma x1 is self-explanatory. X dot x1 is just a sort of dot product over fp to the n. I'll explain why I want that as well in a moment. Now pick x2 and x1 such that qx2 equals 0, and let x2 be the set of x in x1 such that sigma x2 equals x dot x2 equals 0. So this is a linear subspace and it has codimension at most 2. This is a linear subspace that has codimension at most 4, and so on. So this process continues for as long as it can, and in particular it continues while the dimension of xm or something is greater than or equal to 3 or greater than 2. So we can get down to we can get to a point where xm equals, or where 2m equals n minus 2. So we can get to x1 up to xm with 2m greater than or equal to n minus 2, so m greater than or equal to n over 2 minus 1. And what do we have here? We have that, so since xi dot xj equals 0, the xi, or equals 0 if I doesn't equal j, the xi are linearly independent. And since sigma xi xj equals 0 for all ij, whether or not they're equal, Q vanishes on the subspace generated by x1 up to xm. I felt that there was something more I needed to say there, but it seems as though I've managed to partition it into oh, wait a minute, no. So now let's look at a product of, so let V be x1 up to xm. And now let's have a look at sigma. So suppose V1 belongs to V, and that's right, so V1 plus Y, V2 plus Z. So what does that equal? It equals sigma V1, V2 plus, so that bit's 0, sigma V1 Z plus sigma V2Y plus sigma YZ. And that's actually not quite what I wanted. I've realized what I stated was not quite what I wanted to state, so I got myself into a slight confusion. So I don't want to get that sigma is constant on the product of any two of them. I just want to say, so let's just my eraser is not cooperating. Oh, there we go. No, it's not going off again. Okay, such that Q is constant on each of them. So I was trying to prove something more than I wanted. And so let V be, did I call it? I didn't call it anything. So let V be this. So let's get rid of what I just wrote here. And notice the following. So if V belongs to V and X belongs to Fp to the N, then Q of V plus X. So what I'm doing is considering the restriction of Q to capital V plus X. So what does it equal? It equals Q of V plus Q of X plus sigma V of X. And X is a constant here. Q of V is 0. And sigma V of X, that's not a constant, but it's X is constant, so this is a function defined on V, which is just a linear map from V to Fp to the n, so it takes p different values. Well, either it doesn't take p different values, so either this is constant, or we can partition V plus X into P subspaces, affine subspaces, but of codimension 1 inside V plus X, in each of which Q is constant. And so that's why we get n over 2 minus 2, because V itself had dimension at least n over 2 minus 1, but when we partition further one more time into subspaces of codimension 1, we get down to dimension n minus 2. So we are very nearly done now. Let's just go back to what we had here. We had that f correlates with a global quadratic function, but that quadratic function is constant on all of some subspaces in a partition. So first of all, I partitioned into cosets of V, and then each coset of V I potentially partitioned into some more subspaces. So let's actually suppose, just for convenience, that each coset of V I've partitioned into, I don't know, some subspaces V1 plus X up to VP plus X. I don't need this name here, but just it'd be nice to have all the subspaces that I've partitioned into being of the same size. In fact, actually, just yeah, I want them all to be of the same size, just for convenience. So then we have that, going back to the inequality that we had, I just want to make sure I get the notation the same. It was C4 less than or equal to E of X, F of X. I won't call it QZ of X anymore, I'll just call it Q of X. And then by the triangle inequality, so let's suppose my partition is into, I won't use that notation, I'll just say my affine subspaces are V1 up to VR or something, so that's the average over all I of the average over X in VI fx omega to the minus qx, but I chose the VI's such that this would be constant on each VI, so this is actually much easier than the corresponding place in Ross theorem, so that equals the average over I average x in VI f of x. But also remember that f was the balanced function of the set A, so it has average 0. So again, I'm copying what we did in Ross theorem. We also have that 0 equals the average if we don't put the modulus in. Adding the 2, we get C4 is the average over all I of the average of the modulus plus the average without the modulus. And so that implies there exists an I such that the average of f of x in Vi is greater than or equal to C4 over 2. Because this thing is greater than or equal to C4, and this, therefore, this must be the positive rather than negative, and so this is equal to this. So here we go. And that's equivalent to saying that the size of A intersect Vi is greater than or equal to delta plus C4 over 2 times the size of Vi. So what have we managed to do? After a long argument, we started off with the assumption that A has no progression of length 4 and it has density delta, and so that proves that its U3 norm must be not too small, and we've managed to obtain a subspace of dimension roughly n over 2 inside the fp to the n. It was n over 2 minus some small constant, inside which A has density a little bit bigger than delta, and then that allows us to do an iteration argument exactly as in Ross's theorem. And there I'm not going to give the details. I think you will definitely believe me that once we've managed to prove this, it's all over bar the shouting. And so that concludes the proof of Szemerédi's theorem. I feel I should write out what we've proved. So for all delta greater than 0, there exists an n such that for all A in fp to the n, if A has size at least delta p to the n, then A contains an arithmetic regression of length 4. And so it remains for me to thank you very much for following the course if you've got this far. And I will also say I think I've probably run slightly over the time allotted for the course. So if you're taking an exam, then actually I also spent rather a lot of time in the first lecture not doing anything very much formal. But let's just say that for the parts of this video that spill over the 16 hours, I will not expect you to be able to I will not ask you to reproduce very detailed arguments from the very end of the course. So the last sort of half an hour or something, I will not expect very detailed arguments in the exam, although I might ask for something that I might ask for you to demonstrate that you've at least understood the sort of general idea of what was going on. Just because Szemerédi's theorem, this last theorem, was one of the main targets of the course, so I think just having the basic idea of what was going on is something I would like to ask about, or at least have the right to ask about in the exam. So thank you very much, and I will stop.